brain loves a story, or my brain does in particular. And a friend of mine was telling me a good one the other day about a software project he was working on. So he'd been called in to help out with building a company's 5th iteration of its flagship software platform. 5th time's the charm, right? So I was asking what happened to the last 4. He was also having a bit of difficulty because they were building a monolith. And it was quite a big application that was doing a lot of different things, and it didn't necessarily suit being a monolith. It was more suited to being a microservices platform. And the plot thickens. It turns out that the 4th iteration of this platform had been a microservices platform. So I asked, what happened to that? That seemed like a good idea. That seemed like a good fit for this problem. And he said, well, what had happened was the engineers who had been working on the platform previously were really good at building applications. So they'd taken their existing monolith and they'd chopped it into the microservices that would make up the new platform. And they were great at that part. But what they'd neglected to do was think about how to deploy the things. And they left things like containerization until over halfway through the project and choosing Kubernetes to deploy it until halfway through the project. And it turns out that those problems were quite hard to solve later on in the project, and it had huge overspend, and it never saw the light of day. The business lost faith in the project, and it was canned. So the next question then became, why would you do that? Why would you do the easy stuff first and the hard part later? And that was part of the seed for what happened with this talk and why it's here. So, the obligatory who am I slide. Hi, I'm Fahran Wallace. I am a senior consultant at a company called OpenCredo, which is owned by Trifork, and it operates out of London. We end up solving lots of really fun and interesting problems. I tend to specialize in the data space and the architectural space. So you'll see stories from that general sphere sort of scattered throughout this talk, but you're not going to get any particularly concrete, meaty technical stuff in this talk. It's more of a holistic view of some things I have seen and some anti-patterns I've observed throughout my career. So before we do any more about who am I kind of want to know who you guys are. So could you give me a little sort of hand raise, hand wave if you're sort of software engineer by trade, coding, hands-on, day job type thing? That's me. Grand, okay. Anyone more on the business side, more on the organizational sort of sphere, getting things done? Grand, love to see you guys too. Okay, so the ones I'm scared of. Do we have any neuroscientists in the room? Psychologists, people with any sort of formal training in that general sphere? No. Brilliant. All right. So, actually, I say brilliant. I'm ever hoping that a neuroscientist is going to turn up to this talk and tell me what lies I'm accidentally telling you. So I'm a total amateur armchair psychologist. I've read some books, and it really interests me, but it's not my profession. So I've endeavored not to lie to you at any point in this talk about neuroscience or psychology, but if you have any corrections to offer or things to offer, please raise your hand at the end and tell us, because I've done my best, but it's not my expertise. All right, so where is this talk going in particular? So we're going to talk about a thing called cognitive bias. So we're going to go over what that is, why we might have those in our brain, a spotter's guide to the biases of a developer, and then what can we do about those things. So it's going to be some biases and then some ways in which you can see them in your software development role. What's my goal for this talk? I got asked this after the last time I gave it. I think my goal is making people a little bit more aware of how their brain works. Gives people a slightly better chance of spotting when the brain is doing something that maybe will cause them negative consequence in the future. So my hope is that maybe you will spot a pattern and then maybe remember one of the antidotes to that pattern, and maybe it will help you at some point in your future. But there's no great panacea to this. It's just some tools and tricks that I've discovered that have helped me solve certain problems. All right, so the first section. What is a cognitive bias? Well, it's a systematic error in your brain's reasoning. Now, why would we have that, right? There's no good reason that you would want to have that. It's not a desirable outcome. And the reasons are many. It turns out that whilst our brains are extraordinarily powerful for the size they are, you've got about two pints of brain, and I can't think of any other machine that is as powerful for its size. But nevertheless, its memory is finite, its processing power is finite, and there's only so much you can do with it. So you've got to make You've got to make approximations, and you've got to compromise in certain ways, and the brain is really good at making approximations. Other things that have happened to the brain: it had a really, really rough upbringing. It spent hundreds of millennia being chased by predators and learning how to not die to those predators. We've got loads and loads of circuitry that's really good at avoiding lions, but not so much circuitry that's really specifically about programming. And also other things that can affect the way you think. Stress is very, very bad. And you can sort of put people in MRI machines and threaten to immerse their hand in icy water at intervals, and you can see different areas of their brain light up, depending on whether you've stressed them out when you're asking them questions, or whether they're just allowed to relax. All right, so if a neuroscientist was in the room, and they were going to call me out on any slide, this is that slide. This is a quick guide to some areas of the brain that you use in your daily life. Very basic brain model. So the first part is your brainstem. It is responsible for the automatic reactions that your body has that keep you alive. So your heart keeps beating, your lungs keep breathing. It does all of the very basic fundamental, you stay alive. And it's often called the reptilian brain. It's quite an old area of the brain. The next section is called the limbic system, and it's often called the paleo-mammalian center of the brain, and mammals use it quite a lot to make their decisions. It's quite good at making quite fast decisions. It also is your emotional center, so your amygdala is in there, which is the emotional center of your brain and governs quite a lot of how you feel. And finally, the neocortex. That's all this kind of wiggly stuff. When you think of a typical picture of a brain, the wiggly stuff on top is your neocortex. And in particular, your prefrontal cortex is kind of your logical center. And it is really good at really focused, deep thought about a particular topic. So we're going to hop up one level of abstraction here, because the longer I stay in deep neuroscience land, the longer I will misspeak and tell you things that aren't quite true. I'm already generalizing massively about how it works. But the level of abstraction I've chosen is has been taken from a wonderful book called Thinking Fast and Slow by a chap called Professor Daniel Kahneman, who got a Nobel Prize in economics for some of the stuff he discusses in that book. And he posits that there are two areas of the brain, or two ways in which we think is possibly more accurate. Way one is fast. It's called System 1. And it's very, very good at giving you very, very rapid suggestions about what to do and what to think. And then there's System 2, which is slow. And it's very good at reasoning logically about what you should be doing. So the limbic system and the reptilian brain are very, very fast in their reactions, and the neocortex, prefrontal cortex, very, very slow. Well, not too slow, but you know. So what do I mean by fast and slow? Let's just put that in a bit more context. So some examples of fast thoughts you can have. 1 + 1, 2, right? It just pops into your head, and you have no control over whether you think 2 or not. You just know that's the answer. So that's an example of a typically fast thought. Reading var x = 2. If you're a programmer, you'll know that we've assigned the value 2 to the variable x. That happens to you innately and automatically. So it gets slightly more interesting. Recalling feelings about a particular technology. So for example, if a friend comes up to me and says, Fahran, I've got a great idea for a project I want to code with you, and I really want to do it in PHP. I'm going to have a particular response to the language suggestion of PHP that's sort of built up from my experience and from stories people have told me, and I'm going to have this innate feeling towards it, and I can't stop that, I can't control that. That's a fast thought. And also extracting a variable with a keyboard shortcut. I wasn't born able to do that, but through messing around with Java for a good long time, that is a fairly automatic process for me now. So on the flip side then, slow brain, System 2, the thinky part. Finding the bug somewhere in Spring's security filter chain, all gnarly debugging, you have to think really concretely about what you're doing and how you step through things. What isolation level does your database need? Again, hard problem. If you're having to think about that, you probably have to think about it quite in a reasoned manner. It's not going to come automatically to you in a flash. And drawing the architecture diagram of a system. So when I drew that speech bubble, I had an idea. So the first time I gave this talk, I was giving it at a software architecture conference. And I thought, well, I cannot resist this. So this is where I went. I had to go. This is not validated by any professional neuroscientist, but it's my interpretation of what Daniel Kahneman in Thinking Fast and Slow was saying to me. I sort of, as I drew this diagram, came to some somewhat interesting conclusions. So let's start off. We divide our diagram into the things we control, we're trying to model, and the rest of the world. And I guess we interpret the world through our senses. Our ears can hear, our eyes can see. And let's put system 1 on this diagram. So system 1 is that fast and reactive system. And it's got lots of different aspects that are really good at very particular tasks. So if I spot my friend's dog, I'll be like, it's Waffles. If I see my friend Beth, I'll know her face. And that will happen pretty automatically. There's no stopping recognition happening. So system 1 has access to the senses. System 2. I kind of assume that system 2 has direct access to the senses too. I feel like that would make sense. That's not the bit that's particularly interesting to me. This part is the part that's interesting to me. System 2 having access to the suggestions and the inferences that system 1 is making very fast. And system 1 can either make an automatic decision, and system 2 could look at that and say, yeah, I think that's right. I'm going to let autopilot still run this show. Or system 2 can sort of look at the decision system 1 is making and think, I don't actually agree with that. I think I'm going to step in and I'm going to do some manual thinking to work out what the correct outcome is. So here are our actions. So here's an example sort of flow I think might be an approximation of what's going on. So we spot a lion with our eyes. System 1 goes, oh my goodness, it's a lion. let's make the I should run away action circuits light up, and then that's going to be a fairly direct action. So after I gave this talk the last time, a gentleman added something to this, in fact, and he said that there's sort of a message bus that flows around the brain. And if you see, it's got priorities attached to it, so if you see a very high priority item like a lion, that will in fact affect your memory of all the other things, because it will just think, this is the highest priority item, forget everything else, this is the most important thing, which I found very interesting. So what else can system 2 do? So the interaction between the fast system and the slow system is a thing that Mr. Kahneman posits is very important in how we interact with the world, and what cognitive biases happen as a result of that. So system 2 can also train system 1 and sort of tell it what to look for. So for example, if I'm looking for my mum in a crowd, if I'm just looking for her face, that's going to be quite hard. But if I know she's wearing a blue scarf and she's got white hair, I might end up being able to find her a bit better. So system 2 can sort of train system 1 to look for certain things. Also, for example, if I'm fed up by this point of being chased by lions, I might decide I want to learn archery. And that's going to start off for me a very, very slow and manual task, because I have no real idea what I'm doing with archery. But as I do this more and more, and I learn the actions, that will gradually train system 1. So I started thinking of system 1 and system 2. System 1 sort of started seeming like a hot cache of actions you can take and things that are, a hot cache of actions you can take, and you can prime it in certain ways. And system 2 is very good at adding entries to the cache. But actually, cache eviction is a thing it's not particularly good at, as we'll find out later on in the talk. Getting stuff that you've automatically learned to go away again is quite a challenge. All right, so enough of architecture. So here's a question. Are we logical? And by this I mean, which of these two systems is, for the most part, in charge? Which of these is responsible for most of our actions? Is it this fast system 1, which is automatic and a bit sort of rough at the edges, but ultimately takes no effort at all to use? Or is it system 2, which is very, very powerful and very, very logical, but you actively have to take effort to engage? And Professor Kahneman posits that system 1 is responsible for a lot more of our actions than we might intend for it to be. So the second part of the talk then, some of these cognitive biases and getting back more to the world of software development. So don't worry, you can't see this slide. This is pretty much just a wheel chart of the cognitive biases that are readily available on Wikipedia, and someone put them in a nice little circle to illustrate how many of them there are. And that's what I want to kind of show you. There's a lot of different ones, and there's a whole lot of richness in just digging through that list and learning different things about the human psyche. But happily, this guy called Buster Benson put in some effort into categorizing them into sort of 4 general areas. There's not, I don't think, a huge amount of scientific method to that categorization, but it's really helpful for structuring a talk. So I have taken this guy's formatting. So we're going to go through some cognitive biases from the perspective of the world of software development, and we're going to go through them in 4 categories. So the first category is too much information. What you do when there is too much going on and you need to filter that down to something more reasonable about. Not enough meaning. So if you don't know enough about a subject, then what does your brain do to help you patch in the gaps? The need to act fast. So there is just not enough time to make a reasoned decision. So what does your brain do in that time? Or, crucially, your brain feels like there's not enough time, even though there may actually be enough time. And then what should we remember? There's probably a whole talk in that one itself, but that's not this talk. So we're going to do probably 2 biases from each of these. Be 3 and not enough meaning, and then there's 1 at the end, which is extra special, so that gets moved around a bit. All right, so too much information. What do we do when there's too much going on? You're making a decision about your architecture, and you've got too many options, and they're all about the same. So why not form a strong attachment to the first solution you think of? This is a thing called the anchoring effect. So let's do a concrete example. I would like you in your heads to sort of estimate the time it would take for a packet to go and do a round trip within the same data center, let's say in AWS EU West 1, which I think this number is for, a round trip packet time between 2 services deployed in the same availability zone, very, very close together. And is it greater or less than 5 microseconds? All right, so what I did there is I gave you a totally random number, 5 microseconds. It's actually quite a small number when you think about it. And even though you didn't have you know that that's a totally random number, and you probably know at this stage I'm trying to mislead you. But nevertheless, your guess has now been anchored to that number, and you're much more likely to think of a smaller number now that I've suggested this very small number. Because your brain thinks, oh, well, is it safe to go further from this number? No, let's just stick to what we know, even though what we know is totally random and actively misleading. So this happens, I don't know, when you're trying to choose a database, for example, you might draw your architecture diagram, write MongoDB on there, and then just sort of move on a bit. And the fact that you've just written MongoDB there means that you're quite likely to stick to it, even if perhaps something else will end up actually being a better fit for your architecture. So there's also the availability heuristic, which is sort of the colloquialism is when you're holding a hammer, everything you see is a nail. And it's another facet of the same thing. If you've got if something is sort of in this system 1 cache, already primed to go, if you're really familiar with this solution, you're quite likely to just think, yes, well, this is already fresh in my brain, I will use it. And that's not to say this is always a bad thing, right? We're always much more productive with tools we know very well, and diversifying your company's tech stack is not always a good idea. But independent of that, we have this innate bias, which leads us to want to use things we're familiar with above that. So just make sure that reasons A and B, not wanting to diversify your company's tech stack too much and change things too much, and just make sure you're not adding this extra bias in. So something concrete we can do about this. So on a recent engagement I was on, the lead consultant there used a technique because he was sort of seeing this happening. The client was really, really enthusiastic about getting to the build stage of the delivery, which was fantastic. But the downside of that was they were slightly rushing into their technology choice and wanting to get to coding. And so we'd sort of start drawing diagrams of how things will be. And they would choose technologies sort of picked from their cloud provider quite rapidly. And we were sort of struggling to keep up and validate that that was the right choice. So after a little while of this, the lead consultant proposed that we started using the C4 model, which is the 4 C's stand for context, containers, components, and classes. This is a model proposed by Simon Brown, the author of Software Architecture for Developers, which is a fantastic read. And it's one of my recommended reads at the end of the talk. So How it works is you draw these diagrams in order for your system. And if you can't draw a diagram at one level, then you should probably stop and think about that a little more before you go any deeper. So the context diagram is pretty much you draw everything a big box containing everything you intend to build, and then you draw the inputs and outputs of that system. That can be quite a challenge in itself, but that's not the level that's interesting for this aspect. So the container aspect was particularly useful in this case. So when you're drawing containers, you're starting to draw your services and your databases and your individual components. And we found it very, very useful to not just label it with the technology immediately, but to label it with the attributes of that particular flow of data in this case. So, for example, if we needed exactly once delivery between two components, we would say, okay, exactly once delivery needs to happen here, or effectively exactly once. And then after we'd written those constraints in the diagram, then we could validate and say, oh, actually, putting kinesis into Firehose doesn't work here because that doesn't do exactly once delivery. And we were able to validate the architecture a whole lot better after we'd done that. And then you can continue on down to components and classes if you so choose, but I find that having a framework that helps you tackle problems in bite-sized chunks and break things down into smaller problems is really, really helpful for when your brain is jumping to conclusions. All right, so the need to act fast. So remember back to the beginning of this talk when we were discussing that team that had gone for the things they knew the most first. They had written a whole suite of microservices that worked together, but they hadn't worked out how to deploy them because they found microservices applications easy, but they found deployment very hard. So this is a thing called the hard-easy effect. And when we realize that we have a lot to do and the pressure is on, what happens is we want to feel like we've set off running. We want to feel like we're going. And the way we feel like we're making progress is by doing things we find easy and being like, oh, yeah, look, I built this thing. And you can see the building blocks behind you. What doesn't feel very fast is doing very slow research and thinking and reasoning and drawing diagrams and not building anything at all. That feels very, very slow to us, and it feels like we're not making progress. So the propensity for us to do the stuff and get coding very early on in a project is a very sort of real and human need, and it's got at least one project into terminal problems because of that tendency. So what can we do about that? Well, this diagram is very, very simple, but it frames the problem quite well. And it gets a lot across in not very many lines. It's a matrix of value and difficulty. So the headline comment for this is, do the difficult, high-value stuff first, because that will unlock value for your business. So even though deploying your microservices might not be glamorous, it still needs to happen to unlock that value for your business. Second, do the high-value, low-difficulty stuff, because, well, I guess value is the name of the game, right? Do third, dot your I's, cross your T's, add features. And then avoid the high-difficulty, low-value stuff, because it might be risky and it might put the other stuff at risk if it's a high-risk difficulty. But do the hard stuff first. Face your problems. Don't just do the easy stuff and hide from the hard things. So another fun aspect of the need to move fast is that your body wants you to feel confident about what you're doing. And there's this thing called the Dunning Kruger Effect, which is in the late 90s. Well, now Professors Dunning and Kruger were doing an experiment and wrote a paper. And in fact, they got an Ig Nobel Prize for this. The Ig Nobel Prizes being sort of the silly version of the Nobel Prizes. But nevertheless, it's one of my favorite bits of research, I think. What they found is that the more confident someone seems about when they're speaking about a topic, the less likely it is they are to know or be experts in that topic. And vice versa, experts are quite likely to be very unconfident about their topic. So you sort of have this curve here where you've got the path to wisdom and learning and your confidence. You shoot up here, you start knowing things, you start learning things, you go, oh yeah, I know this language, this is great. I understand this new paradigm. And at this point, you reach a very interesting moment. You reach the moment of, all of my unknown unknowns are now known to me. oh boy, I can see the path before me, and it is much bigger than I previously thought. And then you sort of crash down this little pit of despair, and you think, oh no, I can't, I'm not very good at this at all, and then gradually you learn the path to mastery the hard way. I've also evolved much more sympathy for people up here. So I recently took up a musical instrument, never previously played anything before at all. And I had no innate sense of rhythm or pitch at all. And so I started practicing, and I don't know, it sounded like I was getting better. And suddenly, around about here, I discovered that I had, the sense of rhythm kicked in, and I realized I was not playing in time at all. That was very sad for me. But it wasn't, I knew I was bad. You can consciously know you're bad at music, but you can't, you don't have the tools yet to understand why and how precisely you're bad at it. So you can be humble while you're up here, you just don't know any better. The other dark side of the Dunning Kruger curve, as I'm going to call it, despair. So, imposter syndrome, a quite commonly used term in the programming world. And it's basically the feeling that you are inferior to everyone, and everyone else is brilliant and a genius, and much better at your job than you are. And we're all sort of pretending. Everyone has this. All of the best developers I know who I've spoken to about this particular thing say, oh yeah, I always feel dumb. I always need to be going home and learning because I feel like I know nothing. These are like God-tier developers I know. So I think the message for this one is just relax. Everyone feels this. Everyone feels like they're inferior. Because everyone is surfing this curve 1,000 times in their own head all the time. And sometimes you're here, and sometimes you're here, and sometimes you're here. But everyone is pretty all right, and everyone can learn from each other, I think. Oh yeah, also it occurred to me the other night that this looks very much like the Gartner hype cycle. Just the Gartner hype cycle is like for lots of people. Everyone gets very, very excited about a new technology here. Everyone realizes it doesn't solve all their problems, gets very sad, and then they realize how to use the technology, and it starts being used properly. So this is like the Gartner hype cycle, but just for part of an individual's personality. All right, so not enough meaning. What do I mean by that? So the brain is really good at spotting patterns. It is really, really bad at understanding how the patterns came to be about and reasoning about them. So, for example, this is a graph of chocolate consumption per capita and Nobel laureates per member of the population. Now, I could try to persuade my brain that, well, look at this great correlation. Correlation implies causation, right? If I eat loads of chocolate, I'm going to get really smart. That's not going to work. That's not how it works. It turns out that there are confounding variables here. So it turns out that Western countries will quite often win Nobel Prizes. They're often quite affluent, and there's probably quite a strong correlation between education levels and being able to buy chocolate. So that's not particularly interesting. It's not a particularly good story, right? It doesn't really make sense in the brain. So the brain's like, oh, that doesn't make sense. I'm gonna laugh at it. But the trick is when you experience those, and your brain's like, that makes sense. Why not? I'll believe that. So, for example, there was a study done, I think, in the 70s, where ladies who were going through the menopause were given HRT to make that an easier process for them, and so hormone replacement therapy. And it turns out that these ladies later on in life had a greatly reduced risk of heart attacks. And everyone thought, oh, fantastic. I mean, it's quite difficult to work out what the causal effects would be here, but it's all sort of, bodies are confusing, right? We don't really understand how systems work. Maybe messing with people's hormones can give them better cardiovascular health. And this was believed for a little while. But then it turns out that, of course, ladies who take HRT tend to be richer than ladies who don't. And people who are rich have better cardiovascular health later in life. So that's just the confounding variable is money, and they hadn't realized that. But for a little moment, your brain can think, yeah, that's a good story. Someone takes something medical, a medical benefit happens. That's certainly for me, who knows very little about biology, that's a believable story. And the brain loves the story. And when the brain sees a pattern, it will quite often automatically make up a story about that pattern. And then, if it believes that story, if it's a good story, it will believe it. That is one of the truths from Thinking Fast and Slow by Daniel Kahneman, and I've latched onto that because I see it. I see my brain trying to believe stories it's made up a lot. So, cargo cults. A lot of talks about cargo cults go into sort of the cargo cult of agile. That's not quite where I'm going with this. So cargo cults, the origin of the term is in the Second World War, in the South Pacific, there were some native peoples who had not really made a lot of contact with the rest of the world. And suddenly the South Pacific was very busy with planes coming over the Americans, dropping supplies, parachutes, interesting clothes, interesting food, stuff like that. And the islanders were pretty happy about this because they got to experience sort of new bounty from the sky. But the war ended, the planes went away, and the native people were sad. They wanted this sort of free bounty to come back. And so what they did was they had realized that the planes brought the food. So maybe if they tried to encourage the planes to come back by making their habitat the same, so they cleared runways and they laid out flags for the planes, and they built these beautiful models, sort of wickerwork of planes to try and encourage them to come back and bring back the food. And that's the origin of the term cargo cult. They took the cargo from the planes and they made a cult around them. But they didn't truly understand why the planes were there or how they were being helpful to them. And we see this not only in sort of the cargo cult of agile, where people say, oh, you're doing the ceremony of Scrum, but you're not truly being agile. We see it in software practice too. So I wouldn't say involved with cargo cults, certainly experienced one very early in my development career. And it was to do with a particular language. So I was working for a company that was a Java shop. And some of the developers wanted to try out a new JVM language, which was Scala. And Scala is a fantastic language. I do have a lot of time for it still. It's got a very strong type system, a very powerful and flexible type system, which they said would result in fewer tests needing to be written because you can prove that your code is correct as opposed to writing tests for it. And they said that it's a functional language and the functional paradigm is so expressive that it will be faster to write code. And these things are true to an extent. But Scala is sort of like this in my mind. There are a lot of other things you can do with Scala. And the fact that you are using this language that has these attributes does not mean that you will get the benefits of these attributes. And in fact, that project was not well fated. Within 18 months of Git in it happening, that project got torn down and had to be rewritten. And it got rewritten in Java. It was very sad, but it was a very, very interesting lesson in the fact that just because you're using a powerful tool does not mean you'll get the benefits of the powerful tool unless you know what it does and why it works. This is my favorite named bias of them all. This is a thing called the IKEA Effect. And it basically means that things you have lovingly built with your own two hands, you prefer to things that you did not. So you love your IKEA furniture because you built it. So I love my little Frankensteinian test framework that I wrote 3 years ago and really is not appropriate for its work anymore and probably should be killed off. And you too may love your little Frankenstein-y test framework. And it may be that you're very productive in it. And it may be that it sort of found its niche. But nevertheless, we should be aware that we have slightly too much affection for it. The love of a parent as opposed to the love of someone who thinks something's objectively good. And we should be aware of that. All right. So the estimation of time and complexity. I'm not convinced there's an industry in the world that better demonstrates the fact that humans are really bad at estimating time and complexity than the software industry. We are really, really bad at this. But there's a reason for that, it turns out. So one of the things is that humans are really good at thinking and reasoning linearly. And we sort of think chains of actions have sort of linear consequences. And we look back and we don't really see all the complexity that could have happened. We just see what did happen. So, for example, if you have to do 3 tasks on a software project, A, B, and C, and they all take 1 unit of time, you might think, okay, well, that's 3 units of time I have to use to get all that stuff done. And it turns out that because there are intertwinglings, I learned that word yesterday, intertwinglings between the different things you have to get done, that there's hidden complexity between them, so it might take 5 units of time, for example. What other things do we see in this diagram? So it's very difficult for us to sort of see how sort of little tiny decisions add up to this big curve. So this happened, in fact, on the rebuild of that Scala project. We had sort of 3 months to deliver this new bit of software. And it was a checkout application. And the business was being a little bit impatient because it's a checkout, how hard can it be? You take the address, you take the payment information, then you send the item. There's not much complexity. That's not a hard problem to solve. But then we sort of looked at and did a deep analysis of how all the bits fit together. And it turns out that, well, some people don't have addresses because it's just a service. They don't need to have anything posted. They aren't paying for anything because it's a direct debit that happens every month, so it's not an initial payment type of thing. And there were loads of these different cases. And it turns out that there were sort of 58 paths through this checkout, all told. And to make everyone, to get the business to give us a little bit more time to get this done, the technical leaders of that project basically made a spreadsheet of it all, printed it out on A2 paper, folded it up, put it under their arm and said, I know you think this is an easy problem, but here is a physical object showing you the outer curve of all its complexity you asked. Please let us just build it in our own time. And that made that communication, that visual communication, made everything a lot easier, and we got more time to get our stuff done properly. So another thing we do when we're doing our planning poker, I didn't know this until I started writing this talk. We're encouraged to use numbers to estimate things that get gradually bigger. So we start off being allowed to use little tiny numbers, 1, 2, 3, 5, 8 or so, and then they sort of go up, 13, 21, really big numbers. And it turns out that's an effort to get us to factor in this complexity as we're going. We're asked to say, okay, well, a 5 is, you can't have 6. That's just a little bit more. If it's an 8, that means there's going to be a whole load of other stuff you haven't thought of, so let's add that in. All right, so the last section of the biases. What do we remember? There are so many biases about how we remember things. So this is, it's sort of like how the brain compresses memories. Memory is finite, especially our long-term memory. And when you sort of look back 20 years, everything is very hazy. You sort of see some broad brushstrokes, but you don't remember anything particularly in high resolution. So this is a picture of my mum dancing in front of a big, ridiculous Christmas tree. And this is the JPEG compression algorithm's attempt to compress that. I don't really remember much like that at all. I remember that it was Christmas, so I remember being happy, and I'm much more likely to remember happy memories, so I remember it quite strongly. I remember it was Christmas, therefore I think, oh, maybe the air smelled of cinnamon and oranges. I'm not convinced the air did smell of that, but because I've stored the fact that it was at Christmas time, that information comes with it, so the memory is very, very fluid. There's also this wonderful thing called the peak-end effect, and it basically means that you're quite likely to remember the emotional peak of an event, so the happiness or the sadness, and then how it ended. So you'll remember, when you're thinking back on old software projects, you'll think, okay, we had some really tough times and it was really hard, but we got there and everything was all right. But you'll lose the fine detail that made the project and gave you the learnings perhaps to take away from it. So something I quite enjoy doing on projects, and I've seen used to great effect, is using a thing called an architectural decision register. It's a particular type of documentation that's basically an immutable log of things you did and decisions you made. So you don't have all the effort and the faff of going through every bit of documentation and changing it dynamically as you go. Because that's very good at describing what the system currently is. But what it's very bad at doing is giving you the context behind your decisions. And the context behind your decisions is what allows you to evolve your architecture. Because architecture is not a static thing. It's constantly changing with your system. And if you don't remember why it's its current shape, you don't know which bits you can kick over. So I love architectural decision registers. You can just dig back through them and go, oh, that's why the database is like that. I don't need to spend 2 days of my life changing it and realizing, oh no, I can't do that. All right, so this is the final cognitive bias of this talk. And I've kept it to the end because of the peak-end effect, which says that you'll remember things at the end. And this is the one I want you to remember of all of the slides. This is because this is the cognitive bias I hate most in all of the world. And if I could click my fingers and make one go away, this would be it. It's a thing called the Backfire Effect, and it causes quite a lot of damage to the world, I think. So, wouldn't it be nice if, when you encountered a new concept, something that conflicts with some of the things in your little System 1 cache, this fast cache, when you encounter that new concept that is not compatible with your current worldview, wouldn't it be great if you thought, oh, hang on, something's not right here. I'm going to pause, have a little think, engage System 2, and think about this for a while. Maybe evict some of the things from that System 1 cache that aren't compatible, rebuild my worldview, store that. Okay, now we're good. Now we can progress, and we've learned something. Wouldn't it be great if our brains did that? Nope. Our brains do this. Our brains genuinely and physiologically interpret new concepts as a threat. Your blood pressure will raise slightly, your heartbeat will raise slightly, your pupils will dilate a little bit, and your body reacts as if it's under attack, like fight or flight kicks in. You think that this concept is physically attacking you and your worldview, and that needs to be defended. That's not right, right? I hate this, I really do. I think it's so destructive for developers too, because we are very, new information is our lifeblood, right? And we're constantly evolving and trying to absorb new things. And if we've built up a particular concept that now needs knocking down, we're going to fight that, and we shouldn't. There is no quick fix for this. Your brain is going to always react, but I think all you can do is just try to, when you feel this reaction coming in, just think, oh, wait a second, I know about this now. Maybe I can slow down and think and rebuild my worldview a bit. Incidentally, there is a wonderful cartoon on the oatmeal.com, which goes into this in a whole lot more detail, and it's fantastic. That's going to be my one cartoon to take away from this talk. All right, so what just happened? Let's do a quick recap. So what do our brains do when there is too much information? We use heuristics to discard some, and it turns out that we make choices somewhat arbitrarily when we don't have enough, when we have too much choice. When there's not enough meaning, the brain tells us stories based on the patterns we spot. And if it's a good story, your brain will believe that. When we need to move fast, our brain tries to make us feel confident. And we will try to get the stuff we know how to do done first, as opposed to the stuff that is hard and we need to learn how to do. And memory is finite. So we'll remember the emotional highlights, but we won't remember the detail of how we came to decisions. Oh, all right. So what can we do about this? Well, when there's too much information, you can stop and slow down and engage your logical brain. And you can use frameworks like that C4 models set of diagrams to break down the problem into chunks that force you to think about things in a more reasoned manner and not to jump to conclusions quite as fast. When there's not enough meaning, you've got to validate your gut instincts and make sure that if stuff that is cached in your brain does not match reality, try evict that stuff from the cache and reason about it in a bit more of a aware manner. And we need to move fast. Do the difficult, high-value items early. Don't leave the stuff that scares you till later, because that will screw over your project. And we need to remember our reasoning, document and reflect on your decisions. Your memory is never going to remember how you came to an architecture and the full background details behind it. Your only hope is, tragically, writing it down longhand, and then you'll be thankful to your past self. Also, I'm going to sound like your mother here, get enough sleep and avoid making decisions under stress, because that affects the bits of the brain you use to make your decisions. And often they will be worse decisions because of that. So if you want to do any more reading, these are the books and cartoons I would recommend. This is the book, I think, that started me off on this journey. It's a book by Oliver Sacks called The Man Who Mistook His Wife for a Hat. And it's a series of studies of people who have different ailments of their brain, and it teaches you a lot about how the brain works on a human level. I love this book. Thinking Fast and Slow by Daniel Kahneman is fantastic to just leaf through, and every time you'll think, oh, that's how that works, that's why I do that. It's wonderfully eye-opening. And software architecture for developers contains lots of little tools and tricks for breaking down problems smaller, including those C4 diagrams. And the oatmeal comic above is also wonderful for the backfire effect. So that's it. Thank you very much for listening. And if you have any questions, I'll be happy to take them. Thank you very much.